Hi everyone, it's Rachel. This recording is being made for ES 101 and we're going to talk about Kirchhoff's voltage law and define what voltage is and then talk about power. We're going to do a couple of example problems. Should take around 30 minutes. I really appreciate your flexibility with needing to cancel class today. In addition to having a cold this week in general, I am also dealing with some longer term health problems and I'm feeling hopeful that they won't impact our class going forward. Okay, I do want to, since we missed class today, I am hoping to charge ahead, no pun intended. Who am I kidding? I've been thinking about that for like 4 hours, just being honest. But I do want to move forward in our conversation about circuits, just so we can, I'm excited to get to the Arduinos next week, and I want to get going right away on that starting next week. I'm also going to be sort of ending our class a little bit early, as in ending this module a little bit early, and that we'll miss our very last class of the module because I'll be away at a conference. And so we're gonna have a nice day off then, and I'd like to forge ahead for now. Okay, so we'll begin our conversation about Kirchhoff's voltage law with a definition of what voltage is. Voltage is the work per unit charge associated with the motion of charge between 2 points. Now, if you've taken physics recently, you might notice that this sounds pretty similar to the definition for potential energy. If you'll recall, potential energy is when you have a mass that has some height, and because of that height, there's potential sort of stored energy that can be released when that height is sort of dropped. The classic analogy is the car at the top of the roller coaster that has potential energy in it, because when it goes down those roller coaster tracks, it then releases all of that energy. So that's it turns that potential energy into kinetic energy, and so by the time it gets to the bottom of the hill, it's moving very fast, and that energy has changed forms. So you'll often hear voltage called potential, and they're very similar concepts. We measure voltage in volts, where 1 volt is equal to 1 joule divided by 1 coulomb, and then a joule is a unit that we use for work, and a coulomb is our charge unit. Okay, so that's the very basics of what voltage is. And I'd like to now introduce Kirchhoff's voltage law. I always have to be careful. I spelled this wrong. 2 H's. Here we go. Kirchhoff's voltage law. And Kirchhoff's voltage law says that the net voltage around a closed circuit is 0. Okay, so the mathematical formulation of that looks like this. We have the sum. Looks pretty similar to our current law, Kirchhoff's current law. The sum from little n equals 1 up until big N of V sub n equals 0. So that just means as we're going around our closed circuit and our little n starts at whatever element that we're starting on and goes up to the number of total elements in our circuit, we sum the voltages of all of those things together and we should come up with a 0. All right, so let's look at an example of this. Our sort of typical, we're going to get used to seeing this voltage source, and we'll have some elements. That's good, that's enough elements. And we'll go ahead and ground this. Is that enough elements? I think I want one more element. We'll add one more. There we go. And then we'll assign some voltages to these elements. We'll call this V1. These two elements are in series, so they will have the same voltage. We'll talk more about that later. V2, and V3. Okay, and say hypothetically we know most of these voltages, so let's say if Vs equals 12 volts, V1 equals 1 volt, and V3 equals 6 volts. Find V2. Okay. I want to be careful about labeling which way these voltages are oriented, and that'll become a little bit more apparent when we talk about power. But we're going to say that these elements are all dissipating energy from the circuit. So while the source, you'll notice that the source over here goes from minus to plus. Our elements are going to go the opposite way, so they're going to go from plus to minus. Okay. So when we come down here, what our law, applying Kirchhoff's voltage law, KVL for short, what we have is Vs minus V1 minus V2 minus V3 is equal to 0. And then substituting in V2 be equal to 5 volts. Okay. Okay. Now, I mentioned that some of our elements will generate, and some of our elements will dissipate, and they generate or dissipate power. So I want to. The other thing that I want to talk about today is some definition of what we talk about when we talk about power. And what we'll use for power is a convenient definition that's related to the definition that we just came up with for voltage. And what power is it's work per unit time. Okay, so you're doing some work, and that work is happening in an amount of time. All right. So if you've ever had the pleasure of looking at or paying your own electricity bill, you might see on that bill that you're charged for a number of kilowatt hours. The kilowatt is the amount of work, and when you times that by time, you get to the power is the work per unit time. So it's the rate at which electrical energy is being consumed. And so on your electric bill, you might see something called kilowatt hours, and that's what you're being charged for, is kWh. This is kind of an aside. Electric bill. And so what they do is they take that 60-watt light bulb, e.g., if, for example, 60-watt light bulb, and they multiply that 60 watts. This is the power, and that's a per unit time. So they have to multiply that times however long you had that light bulb on for. So if you have a 60-watt light bulb on for 24 hours, then that ends up being 24 times 60. I have a calculator sitting right next to me. Let's see, 1440 watt hours, or 1.44 kilowatt hours. Okay. The hour sign is usually actually lowercase. I'll change that up here. So the power is the power rating that the light bulb is using per unit time, and the total energy that you used is this. So this is energy. That's just an aside because people tend to get those two things confused. Anyway, so what we're talking about is power as equal to work per unit time. And what's convenient as defining power this way is that that's equal to work per unit charge, which we just saw earlier today. That's our definition of voltage, times charge per unit time. And perhaps that's long gone from your brains by now because it's been 2 days, but that was our definition of current on Monday. Okay? So the convenient relationship that we have here is that power is equal to voltage times current. And this will end up becoming pretty important in our network analysis and our analysis of these different circuits. Now, to define power formally, we're going to say that the power generated or dissipated by any element is a product of the voltage across that element and the current flowing through it. Okay, let me take a second and get that down. Okay, the power generated or dissipated by any element is the product of the voltage across that element and the current flowing through it. Now, there are going to be times in our circuit analysis when you're going to be asked to identify whether or not an element is dissipating or generating power. And the method that we'll use to sort of get at that is this sign convention for power. And this is kind of a confusing one, but I think when we diagram it out, hopefully it'll make some sense. So the power dissipated by a load is considered positive. And the power generated by a source is considered positive. So both of those things are considered positive. And let me just quickly diagram out what I actually mean by that. So if we have some voltage source, it should often be labeled with this minus and plus. Okay. And we'll say the current is flowing from minus to positive. Okay. So if it's going from minus to plus, we would call that a source. And because our current is flowing in the direction of the source, we have positive power generated. So power generated is equal to positive VI. Power dissipated, on the other hand, is equal to minus VI. Okay, now let's look at the counter example. So similar setup. And now what we have is a voltage sink instead of a voltage source. So it's dissipating power from the circuit. And in this case, we have our power generated is minus VI, and our power dissipated is plus VI. Okay. So we'll be able to see this in some of our upcoming examples. This can get a little tricky, but hopefully we'll get the hang of it after a few example problems. So we'll take a look at another example, and this one will rely on our new knowledge of power and also on our knowledge of Kirchhoff's current and voltage laws. So sort of bringing everything together here. I'm going to be labeling these different elements. And we'll assign some voltages and some currents that we'll consider as known quantities. So element B is 3 volts, and that goes from minus to plus. We have a known current here, 2 amps. Element E goes the other way, plus to minus. And that's 10 volts. We have a known current of 3 amps down below element D. And we have a known voltage at element C. That's 5 volts. And that goes minus to plus. Go that way. And that's everything that we know going into our problem. Okay? So what we're going to try to do here is determine, excuse me, determine how much power is absorbed and supplied by each element. All right. So the first thing I'm going to do here, I'm noticing that I have 2 known currents, and that leaves me with 1 unknown current. So if you'll notice, we have current in this branch is equal to 2 amps. Oops, didn't need to erase that one. We have current in our middle branch that's equal to 3 amps. But we're missing current in our leftmost branch containing 3 elements. So what we'll do is actually we'll use our KCL from last class to determine the current in the leftmost branch. That's here. Okay. KCL. The nodes that intersect both of those, all 3 of those branches together exist at the sort of top and bottom, where I've just written them in, and we could use either one and either would work. So sort of arbitrarily, I'll choose the top one, and we have 2 amps going out, 3 amps going out, and just for the sake of our positive sign convention, I'll define this one as going out, although I already have an inkling that it might be going the other way. Okay. So doing this, let's see, I'll call that, I can label it anywhere on this loop. I'll label it right up here, call it I1. And then what we have from Kirchhoff's current law is I1 plus 2A plus 3A amps is equal to 0. Then I1 is equal to minus 5 amps. And so that's minus 5 amps going to the left-hand side, or equivalently, I1 equals 5 amps going to the right. And if I check back in our diagram, I've actually already defined it as going to the right? If we sort of let it round that corner, it's already going to the right. So based on how I've drawn the arrow on the diagram already, we've got a positive 5 amps there for I1. Okay, so that's one missing piece of the puzzle. Because I'm looking for power absorbed or supplied by each element, and we're going to find that by calculating the current through and the voltage across each element, we now know the current through all of the elements. So we're going to move on to finding finding the voltage across those elements. Okay, so looking now at KVL, and we can use any closed loop for our analysis. So I'm going to choose. Let's see if I can pick a new pen color here. I'm going to choose to use the outside loop for our first KVL, and I'm noticing that we're going to have to do this twice because we have two unknowns. So this first unknown will be our source, and well, I'm guessing it's a source anyways. I sort of made that assumption because it's in the spot where we usually write sources, but that isn't necessarily true. I am going to write it as though it's a source and use that for our sign convention. So that's element A, and we're going to assume it's going from minus to plus. And what happens is if we get a negative answer after going through our analyses, we know that we've assumed that it goes the wrong way, and we just have to switch the kind of terminals on that. Okay. So KVL, I'm looking at elements A, B, E, and C in that outside loop. So V, A, B, B plus V, C plus, did I get one of them wrong? V, E equals 0. And now we have to be a little bit careful about what our sign convention is. So what we're going to say is anything that goes minus to plus, we'll call that positive, and anything that goes plus to minus, as we're going around the loop in the direction that I've drawn with this green arrow, anything that goes plus to minus we'll call a sink. Okay, so that makes A and B positive, and C and E negative. So VA plus VB, actually I'll go ahead and fill in numbers while we're at this too. So VA plus 3 volts. And then we'll do minus 10 volts. Minus 5 volts is equal to 0. And solving for VA, we get that VA is equal to 12 volts. So because that's a positive number, we were right in our assumption that VA is a source. Had we gotten a negative number here, we would know instead that VA is a sink that is dissipating power from the circuit.